Preparing for an AI engineer interview at NVIDIA Interview. You've reached Candy Mentor, and this video is for you. We'll walk through 15 key questions you're likely to face. For each one, you'll see what the interviewer is testing, the core concepts you should cover, and a sample answer. Subscribe, like, and share, and drop a topic request in the comments. Question 1. Can you explain how self-attention works in a transformer and why it performs well on GPUs? The interviewer wants to assess your understanding of transformer fundamentals, attention computation, parallelism, and whether you can connect model architecture to NVIDIA GPU execution characteristics. While answering, focus on queries, keys, values, scaled dot product attention, multi-head structure, parallel computation, matrix multiplication efficiency, and why transformers map well to accelerated hardware. Self-attention lets each token build context by weighting other tokens in the sequence. I would compute queries, keys, and values. Take scaled dot products between queries and keys. Apply softmax to get attention weights. Then combine values. Multi-head attention repeats this in parallel, so heads learn different relationships. Compared with RNNs, transformers parallelize better on GPUs and capture long-range dependencies more directly, which is why they dominate modern language and vision models. Question 2. If a deep learning training job is underutilizing NVIDIA GPUs, how would you diagnose and improve it? This question evaluates your practical performance engineering skills, profiling discipline, understanding of GPU utilization, data loading bottlenecks, distributed training, and ability to optimize beyond model code. Make sure to cover profiling first, GPU utilization metrics, input pipeline speed, batch sizing, mixed precision, kernel fusion, communication overhead, memory limits, and tools like Nsight or PyTorch Profiler. When training is slow, I first profile instead of guessing. I check GPU utilization, input pipeline stalls, batch size, memory bandwidth, and kernel time using Nsight or PyTorch Profiler. Then I tune data loading, enable mixed precision, increase effective batch with gradient accumulation, use fused kernels, and reduce CPU-GPU synchronization. If scaling across GPUs is poor, I inspect communication overhead, and overlap all reduce with backpropagation. Question 3. What is mixed precision training, and what risks do you need to manage when using it? The interviewer is testing your understanding of numerical precision, tensor cores, memory bandwidth, training stability, and how modern NVIDIA hardware accelerates FP16, BF16, and related formats. In your answer, talk about FP32 versus FP16 or BF16, tensor core acceleration, reduced memory usage, loss scaling, overflow or underflow, master weights, and validation of model quality. Mixed precision training uses lower precision formats for many operations while preserving enough precision for stability. On NVIDIA GPUs, FP16 or BF16 can use tensor cores, reducing memory usage and increasing throughput. The main risks are gradient underflow, overflow, and small accuracy regressions. I would use automatic mixed precision, dynamic loss scaling when needed, keep sensitive operations in higher precision, and compare validation metrics against an FP32 baseline. Question 4. How would you choose between data parallelism, tensor parallelism, and pipeline parallelism for training a large model? The interviewer wants to assess your distributed training judgment, including model size constraints, communication patterns, GPU memory limits, throughput trade-offs, and familiarity with large-scale AI systems. Be sure to mention when each strategy is appropriate, how gradients or activations move across GPUs, memory pressure, communication cost, microbatching, and combining approaches for very large models. I start with the constraint. Is the model too large for one GPU? Or is training just too slow? Data parallelism is simplest when each GPU can hold the model and we synchronize gradients. Tensor parallelism splits large layers across GPUs, which helps when weights or matrix operations are too big. Pipeline parallelism splits layers into stages and uses microbatches to keep devices busy. For frontier models, I would often combine all three. Question 5. Describe the GPU memory hierarchy and why it matters when writing or optimizing AI workloads. This question evaluates your understanding of GPU architecture, memory locality, bandwidth, latency, kernel performance, and whether you can reason below the framework level when necessary. While answering, focus on global memory, shared memory, registers, caches, coalesced access, memory bandwidth, occupancy, and why inefficient memory movement often dominates runtime. GPU performance is often limited by memory movement, not raw compute. Registers are fastest but scarce. Shared memory is fast within a block. Caches help reuse, and global memory is large but higher latency. Good kernels use coalesced global reads, reuse data through shared memory, and avoid excessive register pressure that hurts occupancy. For AI workloads, this matters in attention, convolutions, embedding lookups, and custom-fused operations. Question 6. How would you reduce latency for an LLM inference service running on NVIDIA GPUs? The interviewer is testing your ability to optimize production inference, balancing latency, throughput, memory, batching, model compression, serving architecture, and GPU-specific acceleration techniques. Make sure to cover batching, KV cache efficiency, quantization, Tensor RT LLM or optimized runtimes, speculative decoding, model size, memory bandwidth, request scheduling, and measuring P50 and P99 latency. For LLM inference, I would separate prefill and decode performance because their bottlenecks differ. I would use an optimized runtime such as Tensor RT LLM, enable efficient attention kernels, manage the KV cache carefully, and tune dynamic batching to improve throughput without hurting P99 latency. Quantization can reduce memory bandwidth pressure if quality holds. I would also profile token generation, not just total request time, because decoding is usually the long pole. Question 7. A model's training loss suddenly becomes NaN after several thousand steps. How do you debug it? This question evaluates your debugging process for unstable deep learning systems, including numerical issues, data quality, gradients, optimizer settings, mixed precision, and reproducibility. In your answer, talk about isolating the first bad step, checking data batches, gradient norms, learning rate, loss scaling, initialization, clipping, logging activations, and reproducing with fixed seeds. I would first make the failure reproducible with fixed seeds and checkpoints. Then identify the first step where values become invalid. I would inspect the batch, labels, loss inputs, gradient norms, and activation ranges. Common causes are bad data, too high a learning rate, unstable loss functions, mixed precision overflow, or missing gradient clipping. Once isolated, I would apply the smallest fix and rerun a shorter controlled experiment. Question 8. When would you fine-tune a foundation model versus using retrieval-augmented generation? The interviewer wants to assess your judgment in applying generative AI methods, including cost, data freshness, domain adaptation, hallucination control, and production maintainability. Be sure to mention RAG for external or changing knowledge, fine-tuning for behavior and domain style, evaluation, latency, data security, cost, and combining both approaches when appropriate. I use RAG when the problem needs current, auditable, or proprietary knowledge that should not be baked into weights. Fine-tuning is better when I need the model to change behavior, format, domain language, or task performance consistently. For example, policy documents that change monthly fit RAG, Specialized code generation style may need fine-tuning. In practice, I would benchmark both, measure hallucination and latency, and sometimes combine them. Question 9. How do you evaluate a generative AI model beyond looking at a single accuracy metric? This question evaluates your ability to design robust model evaluation, including task-specific metrics, human review, safety, factuality, regression testing, and production monitoring. While answering, focus on offline benchmarks, golden datasets, human evaluation, hallucination rate, toxicity or safety checks, latency, cost per request, robustness, and continuous monitoring after deployment. For generative models, one metric is rarely enough. I would build a representative evaluation set with expected behaviors, use task-specific metrics where possible, and add human review for quality, helpfulness, and factuality. I would also test safety, bias, prompt injection resistance, latency, and cost. Before release, I would run regression tests against prior versions. After deployment, I would monitor drift, failure patterns, and user feedback loops. Question 10. What is quantization? And how would you decide whether INT8 or FP8 is appropriate for a model? The interviewer is testing your understanding of model compression, inference acceleration, numerical trade-offs, calibration, NVIDIA hardware capabilities, and quality validation after precision reduction. Make sure to cover lower precision weights or activations, memory and bandwidth benefits, calibration, post-training versus quantization-aware training, sensitive layers, benchmark quality, and hardware support. Quantization represents weights or activations with fewer bits, reducing memory footprint and often improving inference throughput. I would choose INT8 or FP8 based on hardware support, model sensitivity, calibration data quality, and target latency. Post-training quantization is faster to try, but quantization-aware training may preserve accuracy better. I would not assume success from speed alone. I would compare task metrics, edge cases, and numerical stability against a higher precision baseline. Question 11. How would you design an image classification pipeline for a real-time application on edge hardware? This question evaluates applied AI engineering across model selection, pre-processing, latency constraints, deployment targets, optimization, and reliability in NVIDIA edge or embedded environments. In your answer, talk about data quality, model architecture, augmentation, validation, Tensor RT optimization, batching constraints, input resolution, latency budget, monitoring, and fallback behavior. I would start from the latency and accuracy requirements, then choose the smallest architecture that meets them. The pipeline would include consistent preprocessing, augmentation during training, validation on real deployment data, and optimization with Tensor RT for the target device. I would tune resolution, batch size, and precision carefully because edge workloads are resource-constrained. Finally, I would add confidence thresholds, monitoring, and a fallback path for uncertain predictions. Question 12. Explain the difference between throughput and latency in AI serving, and how you manage the trade-off. The interviewer wants to assess your production systems thinking, especially serving metrics, batching, queuing, GPU utilization, user experience, and service-level objectives. Be sure to mention requests per second, time per request, dynamic batching, P95 or P99 latency, queue delay, GPU saturation, workload shape, and measuring against product requirements. Latency is how long one request takes. Throughput is how many requests the system handles per second. Increasing batch size often improves GPU utilization and throughput, but it can add queuing delay and hurt P99 latency. I would define service-level objectives first, then tune dynamic batching, model size, precision, and scheduling. The right answer depends on the product. Interactive chat needs low latency, while offline processing can prioritize throughput. Question 13. What steps would you take if distributed training scales poorly from 8 GPUs to 64 GPUs? This question evaluates your ability to diagnose multi-GPU and multi-node scaling issues, including communication overhead, networking, data pipelines, batch size, synchronization, and profiling. While answering, focus on measuring scaling efficiency, NCCL communication, all reduce cost, data loader bottlenecks, gradient accumulation, overlap of compute and communication, network topology, and profiler evidence. I would calculate scaling efficiency first, then profile where time is going. If GPUs wait during all reduce, I would inspect NCCL performance, network topology, bucket sizes, and whether communication overlaps with backward compute. If utilization drops before compute starts, the data pipeline may be the bottleneck. I would also check global batch size, learning rate scaling, stragglers, and checkpoint overhead. The goal is to distinguish algorithmic scaling limits from infrastructure issues. Question 14. How would you make an AI model deployment observable and reliable in production? The interviewer is testing your MLOps maturity, including monitoring, model drift, data validation, rollback strategy, experiment tracking, service reliability, and operational ownership after launch. Make sure to cover input and output monitoring, latency, error rates, resource usage, data drift, model versioning, canary releases, rollback, alerts, logging, and feedback for retraining. I treat deployment as the start of model ownership, not the end. I would monitor service metrics like latency, error rate, GPU memory, and throughput, plus ML metrics such as input drift, output distributions, confidence, and business outcomes. I would version models and data, use canary releases, and keep rollbacks simple. For high-risk systems, I would log enough context to debug failures, while respecting privacy and security constraints. Question 15. Tell me about a time you had to explain a complex AI trade-off to engineers or stakeholders. This question evaluates communication, collaboration, decision-making, and whether you can translate technical trade-offs such as accuracy, latency, cost, and risk into business-relevant recommendations. In your answer, use a clear situation-action-result structure. Explain the technical trade-off. Show how you quantified options, and emphasize alignment, decision quality, and measurable outcome. I would frame the answer around a specific decision, such as choosing a smaller model for production. I would explain that the larger model had slightly higher accuracy, but doubled latency and GPU cost. I would show how I benchmarked both on representative traffic, quantified the impact, and recommended the smaller model with targeted retraining. The key is showing that I can communicate trade-offs clearly and drive an evidence-based decision. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.